We're now starting into our HL topics, and there's only 2 of them, but they're very big. All right, so 15.1 is energy cycles. So we're going back to Hess's law and using the concept of Hess's law and the second law of thermodynamics to understand different reactions that could occur. We're going to first look at lattice enthalpy. For an ionic compound, the lattice enthalpy, which is known as delta H theta lat, so remember that theta sign means it is under standard conditions, and LAT is our designation for lattice enthalpy. So this is the heat energy required to convert 1 mole of a solid salt or ionic compound in its standard state to its ions in the gaseous state. And by putting it into the gaseous state, we can then go through and look at how lattices are built, look at the structures of lattices. It gives us a lot of information about ionic compounds. And so here's essentially the reaction we want to perform. We have sodium chloride solid, and we want to separate it out into sodium ion gas and chlorine ion gas. And the problem is when we try to go through and separate a lattice, usually it'll go just back into its sodium and chlorine and not into its ions itself, let alone in their gaseous state. This value cannot be determined directly, so we make use of changes for which data are available and link them together with an enthalpy cycle. We discussed this with Hess's law. If we know parts or we know indirect roots, we can add it to the whole and figure out what our unknown is. This enthalpy cycle is based on the formation of the compound from its elements in their standard state. And so we're going to do essentially a drawing of what this looks like, since I'm a very visual person. Formation of sodium chloride. Formation equations must produce, again, this should not be new to you at this point, 1 mole of a compound from its elements in their standard states. And they have to be in the standard states because remember, we're looking at the delta H theta. That theta means everything's done in the standard state. So we are going to start with sodium solid. Sodium in a standard state is a solid. We're going to work with chlorine, and remember it's Cl2 because it's a Brinkelhoff, so we only need 1/2 of Cl2, and Cl2 is a gas in its natural state. When those come together, we get sodium chloride as a solid, and that is its standard state. And this is an extremely exothermic process, and the reason that it's an extremely exothermic process is because you create a really strong attraction between the sodium ion and the chlorine ion. And so if you look at their ionization energies and electron affinities, which we'll look at just shortly, you can see that the amount of energy between the two allows sodium to give its electron to chlorine, creating ions and creating a very strong lattice. Okay, so we're going to have this drawing. You don't need to have the number of values off to the side. That's just giving you real numbers. But you want to have this drawing, and we're going to keep adding to it. So you may want to designate a decent amount of page and room to write for this. I think I actually gave myself well over half a page to write all this information. So first we have our sodium. And we're looking at the formation of sodium chloride. So here we have sodium, and in comes chlorine. Yay, right? Boom! We have a lattice of sodium chloride. The energy given off in this process, also known as the delta H of formation, which we covered back in topic 5.2, has negative 411 kilojoules per mole. And that created sodium chloride solid. All right, so that we have been able to measure. So we have our delta H of formation. Okay, remember, keep a spot for that and write everything else off to the side. So the lattice enthalpy is the energy required to take this 1 mole of a compound and separate it into its gaseous ions. This is an endothermic process, but it is difficult to measure directly and it's really hard to do it. Therefore, we're going to do this in steps. So going back to the chart that we have created, we are going to look at the lattice enthalpy for sodium chloride. So our goal is to make sodium ion gas and chlorine ion gas. As you can see, it is much higher in energy than the original sodium and chlorine gas, or sodium and chlorine elements in their standard states, and of course the sodium chloride solid. So ideally, we're going to keep the ions as their ion form. We're just going to separate them. So we're essentially breaking the bonds, and we're just looking at how much energy is in that attraction between the negative chlorine and the positive sodium, so on and so forth. And so what we're going to be looking for is that delta H of the lattice energy. So what energy is right here in between each of these ions? We know how much energy is released when it forms, but we don't know what it is individually between each of those guys. So how do we go through and solve this then? And this is called the Born-Haber enthalpy cycle. Since the lattice enthalpy is difficult to measure directly, its value is calculated by using an energy cycle, just like Hess's law. And the Born-Haber is just this specific, looking at lattice enthalpy. All right, so we're going to go through and we're going to add a lot of information now. So we know about the formation of sodium chloride. Right, so we're going to take solid sodium, react it with chlorine gas to create sodium chloride. Okay, so we're going back to the beginning. We already know about the formation of sodium chloride, so on and so forth. When we go through, so we have our sodium, we have our chlorine. The first thing we want to do, and please ignore this number for right now, it came a little too early. The first thing we want to do is the atomization of sodium. All right, so sodiums are gray dots. So we want to separate a solid sodium into separate gaseous sodium ions, or sodiums. So this is called the delta H of atomization. So we're going to take solid sodium, as you can see, the solids in red, and we are going to turn them into gaseous sodiums. So you can see that change right here. That is a positive 107 kilojoules per mole. So it's an endothermic process. We have to put energy into separating each of the sodium atoms, which makes sense. Next, we have this little problem with Cl2, right? Okay, so we only need 1 chlorine total. So we need to break that bond between the chlorine atoms because they are Brinkhoff. We want to separate those guys, right? So what we're going to do is we're going to use bond enthalpy to separate them. Okay, and so that bond enthalpy is looking at 1/2 of 242. Why is it 1/2, I ask you? Well, how many chlorines do we need? We only need 1 chlorine, so we need to get rid of that 2. You need to be very careful when doing this though, because that bond enthalpy. What if we were working with magnesium and it's magnesium chloride? That is MgCl2. We'd need both chlorines. They still have to be separated, okay? But we would not need that value of 1/2. So really pay attention to what it is you're writing down. Okay, so now we have atomized our sodium from a solid to a gas. We have split our Brinkhoff Cl2 into an individual Cl. So now what we want to do is we want to create our ions. And so this is the first ionization of sodium. Remember, ionization energy is the energy required to remove 1 mole of electrons to create a positive ion. All right, so there goes the electron, whee, and we create a sodium ion. This is called the delta H of ionization. Ionization is making an ion from a metal. That has a value of positive 496 kilojoules per mole. All right, so now we made our sodium ion, and we have that electron kind of floating around, right? Okay, so now that we have made a sodium ion, we need to make a chlorine ion. So this is called the first electron affinity of chlorine. Remember, electron affinity is when 1 mole of electrons is accepted by 1 mole of gaseous atoms, right? So the first electron affinity is the enthalpy change when 1 mole of gaseous atoms attracts 1 mole of electrons. So that electron from sodium is like, sup, chlorine, right? Now we have chlorine negative. And you can get this value in table 7 in your data booklet, or it may be given to you. But all this information, with the exception of atomization, can be found elsewhere and or calculated. All right, so chlorine accepted an electron. And so we have a negative 349 because if you think about it, it's forming a bond and therefore energy should be released. Again, you need to be very careful. What if this was O, and O has a 2 negative charge? So it actually needs 2 electrons. So you would need to use the delta H of electron affinity for the first electron and for the second electron. Really pay attention to charges, right? For that electron affinity, you may have 1 or 2. The same goes for delta H of ionization. You may have, if you have Mg2+, right? That means you have to get rid of 2 electrons, which means you have 2 values you need to incorporate in that calculation. Really pay attention to the details in these numbers. So now we have made each of our individual sodium gas ions and chlorine gas ions, right? So now we can figure out that lattice enthalpy for sodium chloride because we've figured out each of these individual steps. All right, so again, our whole purpose is we have our solid sodium chloride. We want to separate them into their gaseous ions, not into their separate standard state elements, but actually the gaseous ions. So we know, at this point, we know our delta H of formation. Okay, we know our delta H of atomization. We know our bond enthalpy for chlorine. We know our delta H of ionization. We know our delta H of electron affinity. We know everything but the delta H of lattice enthalpy, right? So if we know everything, and this is a cycle, no one arrow goes astray, right? So based off Hess's law, we can solve for this one unknown. So how do we go about doing this? So we have a calculation. We have delta H of formation. And we just go through and we add everything up. So we have delta H of atomization plus bond enthalpy plus delta H of ionization plus delta H of electron affinity minus delta H of lattice, because that arrow, if you go back and look at your picture, this is really the only arrow that goes in the opposite direction with the exception of delta H of formation, which is on the other side of the arrow. Now, what is our unknown here? Well, delta H of lattice, right? So that's our unknown. So we can go through and figure and reform this calculation. So delta H lattice equals, rewrite it all, delta H of atom, which is our first arrow, plus enthalpy, second arrow, plus delta H of ionization, third arrow, plus delta H of electron affinity, fourth arrow, minus delta H of formation, because it goes in the opposite direction from all the other arrows. And so it's a minus. I'm going to remind you again, because this error happens a lot. For ionization and electron affinity, make sure you look at the number of electrons, and you need to use the appropriate numbers, right? If it's only one electron transfer, is it 2 electron transfers? Make sure you're using accordingly. Look at this bond enthalpy. Do we just need 1 Cl, or do we need 2 Cls? If it's 1 Cl, you need to half the value of bond enthalpy because you only need one of the two. If it's 2 Cls, you need the full. So make sure you're really paying attention to these details. All right, so going through, if you look at your chart, we have all these values. So the delta H of atomization is positive 107. We only need 1 chlorine in this instance, so we need half of the positive 242 because we're breaking, not forming. We have only 1 electron being taken from sodium, so we have 496. We have 1 electron being accepted by chlorine, and it has a negative value because it's forming that quote-unquote bond. And then we have our delta H of formation, which is 411. Do the math, right? You get positive 786 kilojoules per mole. Our arrow was going up, was it not? So we know that to turn a solid sodium chloride into its gaseous ions, we're going to need to pump in energy to make this happen. All right, so theoretical lattice enthalpy. This takes a lot of work to actually go through the process of lattice enthalpy. So we have some computer models that we can use, and this is called the ionic model. And the ionic model is only the when they go through and figure it out based on calculations and behavior, the ionic model is only the attraction that is due to the electrostatic forces between ions itself. It doesn't take anything else into account. So trends in lattice enthalpy, and that means the energy needed to separate those ions depends on your ionic radius, right? So if your ionic radius increases, right? So you're increasing the radius. The atom is getting bigger. The attraction, therefore, between two atoms is going to decrease. So the larger the atom, the less attraction there is between each individual atoms. Ionic charge. As you increase the charge, so +1 to +2 to +3, you are going to increase your attraction. And the reason being is you are creating, if you're looking at a metal, so like sodium +1, magnesium +2, aluminum +3, and you're going through and looking at each of those, aluminum has the strongest attraction because it lost 3 electrons. So you have a much higher effective nuclear charge on aluminum, which means you're going to have a much stronger attraction to the nonmetal in which it is attracted to. Both play in something's attraction, or in two atoms' attractions to each other. The theoretical values can be calculated once a geometry of the lattice is known, so on and so forth, all within the computer model. So here you have just a bunch of different values. You have a much more simple table in your book, but this kind of just gives you an idea in looking at trends, right? So we are going from lithium to iron 3+, and you can see from lithium to iron 3+, the energy really is increasing significantly due to that attraction. And that is going to, again, be due to, if you look at the charges, you're increasing the charge, so on and so forth. But it's not a linear fashion, as you could probably tell. And it's almost an exponential fashion in parts. And the reason being is we don't take into account the covalent properties of ions, right? So even though you're not making a covalent compound, you still have all those electrons there. So you are actually starting to get some London dispersion forces occurring, and you have IMFs showing up. So not only do you have the ionic bond, the electrostatic attraction between ions, you have, due to electrons being present, London dispersion forces. So the more electrons you have, the stronger your force. So even though iron has a really large radius, relatively, in this table, it still has a strong lattice enthalpy because it is participating in those covalent properties of that is created in your London dispersion forces, so on and so forth. All right, so enthalpies of solutions. Enthalpy of solution. So this is an enthalpy change when 1 mole of solute, so that is what is being dissolved, is dissolved in a solvent to infinite dilution under standard conditions. So we are making a huge assumption that the particles spread as far apart from each other as possible, and they are essentially completely absorbed by the solvent. As we know, or you should know at this point, ionic compounds readily dissolve in water. You're like, well, why? I need a refresher. Well, water is a polar solvent. Right? So, in our water, we have HOH. Due to polarity, right, our H's have a slight positive charge, our O has a slight negative charge, so on and so forth. So our positive H's are attracted to a negative ion. Our negative oxygens are attracted to a positive ion. And because of that polarity, ionic compounds are going to be picked apart by water molecules. And that is what's happening when you have dissolution, or you're dissolving a salt in water. Hydrated salts are salt ions surrounded by water. And you've actually worked with these before, looking at hydration values, so on and so forth. Now we're just looking at what happens when you have a hydrated salt. So hydration enthalpy is the strength of interaction between water and ion. So we've been looking at just what is the strength between ions in a lattice. What if we throw water in there too, right? And so now we have a hydration enthalpy. So now we have not only the ions attraction, but now we have an attraction of water to the ions. And how does that affect what it looks like? So this is force of attraction between the water and ion is exothermic. So you can kind of take a look at the table below, but what this is looking like is group 1 cations, group 2 cations, your halide ions, they're all negative. So lithium in its attraction to water has a value of negative 519 kilojoules per mole, so on and so forth. You increase the charge, you increase radius, you can look at what those effects are and you can predict trends. So the value is less exothermic as groups descend. As you can see, lithium has a much higher value than cesium. Why? Think of radius. Your ionic radius is increasing. There's going to be less attraction, effective nuclear attraction of that atom to the water. Okay? Then as you go across, so if you just look at sodium to magnesium, we go from negative 404 to negative 1931. The metals become more exothermic. You're increasing your charge, which we've already talked about with the theoretical lattice enthalpies. So you're increasing the charge, and when you're increasing the charge, you're decreasing your ionic radius. So you're increasing the effective nuclear charge and therefore creating a stronger attraction. So these values are what are called the delta H of hydration. And this is when your enthalpy change when 1 mole of gaseous ions from a salt lattice is dissolved to form an infinitely dilute solution. All right, so what we are looking at is the delta H of solution of sodium chloride equals your delta H of lattice of sodium chloride plus the delta H of hydration of your sodium ion and the delta H of hydration of your chlorine ion. So what this looks like, we're going to go back into an energy cycle. So we have our delta H. Here, we have our sodium chloride solid. We have already gone through and calculated what it takes to turn sodium ion gas and chlorine ion gas, right? So we already have that value. And so we have our delta H lattice. And we calculated that before, and we came out with 790 kilojoules per mole, right? Okay. So then we want to turn these guys into an aqueous, and we want the ions to be aqueous. So we have sodium aqueous plus chlorine aqueous, and this means they have been hydrated, right? So we have the sodium chloride solid going to aqueous, and we have these gas states being dissolved essentially into an aqueous, and those are those hydration values. So we have delta H of hydration. For sodium, and this value can be found in table 20 of your data booklet, and that is going to be negative 424 kilojoules per mole. We have delta H of hydration of our chlorine ion, and that's negative 359 kilojoules per mole. So we can solve for the delta H of solution for sodium chloride. So how much energy is there when you create a solution, right? And so you can go through and you can calculate all the values you need. So plug in your numbers, right? So our lattice, positive 790. Hydration of sodium, negative 429. Hydration of chlorine, negative 359. And that is going to equal a positive 7 kilojoules per mole, right? Now, if you look at section 19, table 19 in your data booklet, it actually gives you values of true aqueous solutions, and sodium has a positive 3.88. We're off by a lot, so you could actually be asked to calculate your error, right? And give reasons why it would be so off. And the same reasons apply as we have discussed before. And the disagreement between the positive 7 and the positive 3.88 illustrates a general problem when you have a small numerical value that is calculated, so our answers, from a difference of very large numerical values to begin with. And so when you have such large values, you're increasing your room for error, which can occur.